So, we are back at the desk, the coffee is freshly brewed, and the lava lamp is officially on.
It is definitely on. The vibe is set.
We are treating this session completely like a late-night study group. Just you, me, and a stack of O'Reilly books that are, frankly,
Thick enough to stop a bullet.
literally, so heavy. But that is the vibe.
It is. We are taking the intimidation factor completely out of computer science today and just talking through the foundational papers. No jargon without a proper explanation, no gatekeeping, just the good stuff.
Exactly. Just breaking it down. And before we even crack open the source material today, I really have to give a massive shout out to one of the regulars in our study group.
Oh, yeah, for sure.
Dragos, who just aced his multi-agent systems exam.
That is huge. Multi-agent systems are incredibly complex.
So tough.
Yeah. Congratulations to Dracos. Seriously impressive.
We absolutely love to see it. Keep sending us your wins, guys. Okay, so let's get into the material for this deep dive. Last time we talked about distributed systems sort of in the abstract.
Right, the theory.
Yeah, but today we are looking at the specific architecture that effectively built the modern big data landscape.
Yeah.
We are talking about Hadoop and HDFS.
The Hadoop distributed file system. And I know for some people, hearing the word Hadoop feels a bit like, I don't know, looking at a scheme engine in the age of electric cars.
Right. It feels a little bit like history class.
It does.
Yeah.
But you really can't understand the modern cloud. You cannot understand Amazon S3 or Azure Blob Storage without understanding the steam engine that started it all.
You have to know the roots.
Exactly. If you look at the source material we have today, specifically the HDFS architecture and design paper, and the original Google file system paper from 2003, this is the blueprint.
The 2003 GFS paper is basically the spiritual ancestor of everything we're talking about today, isn't it?
It totally is. That was the moment the industry sort of collectively realized you don't need a massive supercomputer to process huge data.
You just need a lot of cheap computers.
Right. Cheap, unreliable computers and a really, really smart file system to glue them all together.
So let's set the scene using Hadoop, the definitive guide. What is the fundamental problem we are actually trying to solve here?
Well, the problem is just physics, honestly. Specifically, the physical limit of storage.
Okay, walk me through it.
Let's say you have a data set. Maybe it's all the web logs for a massive search engine, or it's genomic sequencing data. And it starts at, say, 500 gigabytes, then it hits 2 terabytes, then a petabyte.
And eventually you can't just go to the electronics store and buy a bigger hard drive.
Exactly. You hit the hard ceiling of what a single machine can physically hold. So you really have no choice but to partition that data across a network of machines. You have to spread it out.
But as soon as you spread it out, you introduce this absolute nightmare scenario. Because, I mean, if you have one computer, it might crash once every 3 years. But if you have 1,000 computers...
Something is broken right now.
Always.
Always. And that brings us to the core philosophy of HDFS, which I absolutely love. It's stated right in the architecture and design paper. It says hardware failure is the norm rather than the exception.
It's such a pessimistic worldview,
Yeah.
but it's so practical.
It's highly realistic. HDFS assumes the hardware is basically garbage. It assumes components will break, a hard drive will fail, a switch will die, a power supply will just smoke itself.
Just spontaneously combust.
Right. The system is entirely designed with the assumption that the underlying infrastructure is unreliable, so the software has to be the safety net.
Which is a perfect segue, actually.
Yeah.
Because if the system is designed to handle that kind of daily chaos, it needs a leader. It needs a boss to manage the mess.
Ah.
And that brings us to...
Oh, no. I see where you're going with this.
Oh, yes. It is officially time for our Japanese word of the day.
I cannot believe we're doing this in a serious study session.
We are doing this. It is happening. Today's word is Hokage.
Okay, let's unpack this. Why are we talking about anime right now?
So Hokage literally translates to fire shadow. But if you've seen Naruto, you know it means the absolute boss of the village, the leader. The one who makes the high-level decisions but doesn't necessarily go out and, like, scrub the floors or do the grunt work.
And please connect this to distributed file systems for me.
Which is exactly what the Namenode is.
Yeah.
The Namenode is literally the Hokage of the Hadoop cluster. It doesn't do the heavy lifting, but it tells all the datanode ninjas exactly where to go.
You know, I hate to admit it, but that's actually a surprisingly accurate analogy.
Thank you. I thought about it a lot.
No, really. In HDFS architecture, you have this strict master-worker pattern. The Namenode is the master, the Hokage. It manages the entire file system namespace.
So the directories, the file names.
Yes, it keeps the tree of files and directories in check.
But it doesn't store the actual data, right? That's the key distinction.
Exactly. The name node does not do the heavy lifting. It doesn't store the actual bytes of your movie file or your server log. It just knows where those blocks are. It tells the data nodes who are the ninjas in your scenario.
The minions.
Yeah.
Yambu Black Ops, they do the dirty work.
Right. The name node tells the data nodes what to do. It says, you store this block, you replicate that block over there. The data nodes are the workhorses. The name node is purely management.
And there's a really scary part to this too, based on the papers. The name node holds all that metadata, the map of where absolutely everything is in memory. Like in RAM.
Yes. Which means if the name node vanishes,
the village falls.
The file system is effectively lost. You might have 10 petabytes of data sitting perfectly safe on those drives, but without the name node to tell you which block belongs to which file, it's just digital noise.
It's just a bunch of random ones and zeros.
Exactly.
Also, I am 100% sure I just butchered that pronunciation. Hokage. I am so sorry to our Japanese listeners. Please drop into the YouTube comments and roast my accent. I completely deserve it.
You really do. But let's stay on this idea of the Hokage or the name node protecting the system, because security and stability are huge themes here.
Oh, speaking of protection, I actually had this debate with my roommate the other day, and we need to settle it right now. We were talking about DDoS attacks on a server rack.
Is this the detour?
This is the detour, the Hokage protocol. Okay, here is the scenario. Massive DDoS attack incoming, millions of packets flooding the network. Who do you want as your lead sysadmin? Goku from Dragon Ball Z or Vegeta?
This is ridiculous.
Just answer. I say Goku. Goku's the ultimate solution. He sees the packets coming, he screams, he goes Super Saiyan 3, hair everywhere, lightning, and he physically punches the server rack to stop the packets. It's brute force mitigation.
That would physically destroy the hardware. That's not mitigation, that's just permanent downtime. You've bricked the server.
But it stops the attack. 0 packets are getting through a smashed router.
No, see, this is exactly why Vegeta is the superior choice for a system administrator.
Good on? Convince me.
Vegeta would act as the firewall. He wouldn't stoop to touching the hardware. He would stand there with his arms crossed, floating slightly, looking down at the incoming traffic. He would aggressively block IP addresses out of pure spite and pride.
Out of pride. I love that.
He'd be saying, you are not worthy to ping this port, and just dropping packets left and right.
Okay, that's entirely fair. Just a final flash on the subnet mask.
Exactly. Though, honestly, I have to point out they are both terrible system administrator.
True, but Vegeta is slightly more logical. I will concede that.
Thank you. Can we please get back to the file system now?
Yes, yes. Back to business. Actually, before we get into the heavy technical mechanics of how the data is actually stored on the disks, I want to throw a challenge out to the listeners.
Now a mid-episode quiz.
A mid-episode quiz. Hey, TA listeners, quick pop quiz. In HDFS, what is the default block size for Hadoop 2.x, and why is it so large? Drop your answers in the comments.
That's a really good one. It connects directly to the underlying performance model of the whole system.
Think about it, guys. We'll reveal the answer in just a few minutes.
So while they are thinking about that in the comments, let's talk about that specific word, blocks.
Let's do it, because when I think of a block on my normal laptop hard drive, I'm thinking tiny, like 512 bytes.
Right. Standard disk blocks on a regular OS are usually 512 bytes, maybe 4 kilobytes, but HDFS operates on a totally different scale.
So let's answer the quiz. How big is an HDFS block?
The default in the earlier versions, and widely cited in the 2.x documentation, is 64 megabytes. And in many modern production clusters, it's pushed up to 128 megabytes.
128 megabytes. That is massive. That is literally millions of times larger than a standard disk block. Why make them so incredibly huge?
It comes down to one specific trade-off that the designers had to make. Seek time versus transfer rate.
Okay. Let's unpack this slowly. This is crucial to understanding why Hadoop is actually fast for big data.
Okay, think about how a traditional spinning hard drive works. It has a physical arm and a magnetic platter. To read a piece of data, the arm has to physically move across the disk to the right spot. That physical movement is the seek.
And moving physical metal takes time.
It does. Let's say it takes about 10 milliseconds, which sounds fast to humans, but in computer time, 10 milliseconds is an absolute eternity.
Right, the CPU is just sitting there waiting.
Exactly. Now, once the arm gets there, it starts actually reading the data. That's the transfer. Transferring is relatively fast, maybe 100 megabytes per second.
So the goal is to spend most of your time reading data, not moving the arm around looking for data.
Precisely. If your blocks are small, like on a normal laptop, you are constantly moving the arm. Seek, read a tiny bit, seek, read a tiny bit. It's highly inefficient for massive files. You want the seek time to be negligible, ideally about 1% of the total transfer time.
I see the math here. So if the seek takes 10 milliseconds, you want to be reading continuously for at least 1 full second to make that seek time, quote-unquote, worth it. And at 100 megabytes per second, that means you need a block size of
around 100 megabytes. Hence, the 64 megabyte or 128 megabyte default block size. It allows the system to operate near the raw speed of the disk drive, streaming data continuously, rather than jumping around like a vinyl record player.
That makes total sense. It's like moving house. You don't want to carry one single sock at a time to the moving truck. You want to pack a massive box of blocks so you only need to walk back and forth once.
That's a great analogy. And this abstraction brings another huge benefit. Because the file is broken into these independent massive blocks, a single file can actually be larger than any single disk in your cluster.
Right. You could have a 10 petabyte video file, and HDFS just happily scatters the blocks across 1,000 different drives.
Exactly. And this leads directly to the concept of splits and data locality. The definitive guide mentions that Hadoop does its absolute best to run the map task on the specific node where the data actually lives.
The famous rule, moving computation is cheaper than moving data.
That's the exact quote. It's so much faster to send a tiny 10 kilobyte Java program over the network to the server that has the data than it is to pull gigabytes of data across the network to where the program is.
Okay, so we have these massive blocks scattered everywhere across the network.
Yeah.
But we established earlier that hardware failure is the norm. The hardware is garbage. So if my data is on node 42 and node 42 catches fire, my data is gone.
It would be. If we didn't have replication.
Ah, the safety net.
The ultimate safety net. The standard replication factor in HDFS is 3. That means every single block of your data exists in 3 distinct places at once.
So if a data node smokes itself, I'm still good.
You're totally fine. But it's not just random placement. They don't just throw the copies anywhere. This is where the architecture gets really clever. The HDFS architecture paper describes a strategy called rack awareness.
It's one of my favorite parts of the paper. It's so strategic.
It is. Here is the default strategy. Replica 1 goes on the local node where the writer is, the machine you're interacting with. That's purely for write speed.
Okay, makes sense.
Replica 2 goes on a different node, but in the exact same rack.
Okay, stop there for a second. So, if the first node fails, we have a backup physically close by. That means fast recovery because the network traffic stays inside the rack. It doesn't have to cross the whole data center.
Exactly. But here is the critical failure scenario you have to plan for. What if the top of rack switch fails? Or what if the power supply to that entire rack goes out?
Then you lose node A and node B. You lose replica 1 and replica 2 simultaneously, you're toast.
Which is exactly why replica 3 goes on a node in a different rack entirely.
It's genius. So you beautifully balance the write speed because writing inside the same rack is super fast with long-term reliability. You could literally lose an entire physical rack of servers and still have your data sitting safely on that third replica in a completely different aisle of the data center.
Precisely. It's all a probability game. The odds of a single node failing are very high. The odds of a whole rack failing are lower, but still definitely possible. But the odds of 2 different racks failing simultaneously, very low.
Now, how does the Hokage, the name node, know if a ninja has died? How does it know when to trigger this recovery process?
It listens for a heartbeat.
A literal heartbeat.
A digital one. Every 3 seconds, every single data node sends a tiny signal to the name node over the network. It just says, I'm here, I'm alive, here are my blocks.
And if the heartbeat stops, if a node just goes silent,
the name node is patient. It waits. It doesn't want to panic and start copying massive amounts of data just because of a tiny network blip. But if it doesn't hear a heartbeat for 10 full minutes...
he calls it time of death.
It officially declares the node dead. It looks at its internal map, sees exactly which blocks were on that dead node, and immediately instructs other healthy nodes to create new copies to get the replication factor back up to 3.
So the system literally heals itself.
Automatic self-healing. It's beautiful engineering.
It is beautiful, but, nothing is perfect. We talked about the name node being the single point of failure earlier. But looking at the Shachko Scalability Update paper, isn't it also a massive bottleneck for the whole system?
It really is. And this is the limitation that eventually forced the Hadoop architecture to evolve over time.
Right, because the name node keeps all that metadata in RAM.
And RAM is finite. The Shachko paper notes that a standard name node, heavily optimized, can handle metadata for about 100 million files.
100 million sounds like an insane amount of files to me.
It does, until you are Yahoo or Facebook or Google. If you have billions of files, especially if they are small files, you fill up the Namenode's memory extremely fast. You crash the Hokage.
You just overload the boss with too much paperwork.
Exactly. And the crazy part is, once the Namenode's memory is full, you cannot write a single new file to the cluster, even if you have petabytes of empty physical disk space on the data nodes. The brain is full, so the body can't move.
That is a serious design flaw. So how did they eventually fix it?
Two main ways in the later updates. First, HDFS Federation. This was introduced in release Rel 2.3.
Federation. Sounds very Star Trek.
A little bit.
Yeah.
Basically, instead of one Hokage, you have multiple. You partition the file system horizontally. One name node strictly manages the /user directory. Another manages /data. Another manages /logs.
Oh, I get it. They all share the same pool of data nodes underneath, but the namespace management is split up. So multiple Hokages for different districts in the village.
Exactly. It scales the management layer out. And the second big fix is high availability, or HA. This directly solves the single point of failure problem we joked about earlier. You run two name nodes, one active and one standby.
So if the active one crashes?
The standby takes over almost immediately. They share a highly available edit log, so the standby is always perfectly up to date with the active node.
That seems critical. I can't imagine running, like, a bank or a hospital system on this without HA.
In the very early days, they effectively did. It was a known risk. But yes, for any modern enterprise use, HA is absolutely mandatory.
Wow. So let's step back and look at the big picture here. We've covered a lot of ground today.
We really have.
To recap everything for everyone listening, HDFS is the storage layer. It's designed for massive files. It is written once and read many times. It runs on commodity hardware stuff that breaks constantly, and it survives because it relentlessly replicates data 3 times across different racks.
And it's all ruled by a centralized name node that manages the map but never actually touches the cargo.
It's an incredibly resilient system. But I want to leave you with something to think about, something a little provocative before we wrap up.
Go for it.
We talked about how the name node is the ultimate bottleneck because it's a single server maintaining a hierarchical file system structure. Look at the Schwarzkopf paper. He raises a really interesting point. If the file system namespace is the bottleneck, why are we using a file system structure at all?
Haha, that is the billion-dollar question right there.
Right. Why not just replace the name node with a distributed database?
And that is exactly what happened next in the actual evolution of big data. Google eventually moved away from GFS to something called Colossus, which uses a distributed database to manage all that metadata. And in the open source Hadoop world, people started looking at using HBase to manage the namespace instead of RAM.
It effectively removes the limit entirely. You can have billions and billions of files because the map itself is now distributed too.
It does. It completely shifts the paradigm from files and folders to objects in a database. But that is a deep dive for another day.
Absolutely. We will save Colossus and Bigtable for a future session.
I think we've melted enough brains for one day.
Agreed. All right, TF family, that is it for our deep dive into HDFS. We really want to know what you want to learn next. Should we do MapReduce to follow this up? Should we jump straight into Spark? Or maybe we go completely different and do some core cybersecurity?
Definitely let us know in the comments.
Drop a comment, and don't forget the golden rule of the internet, SSL.
SSL.
Subscribe, share, and like.
Oh, man. That was terrible. That was a terrible security pun.
It's the protocol. We have to follow the protocol. Thanks for listening, everyone. We'll catch you in the next study session.
Bye, everyone.